This is going to be the first lecture on class 11 maths chapter 2, that is on the relations, and these are the points I am going to discuss in this video. First is about ordered pairs, then equality of ordered pairs, Cartesian product of sets, relations and number of relations, and then domain and range of relations, and also codomain, and then at the last I'll explain how a relation can be written in different forms. That means different forms of writing a relation with example. Now starting with the first point, that is ordered pairs. Any two elements written in a specific order and enclosed with first bracket, example say 2 3, these two numbers written in a specific order 2 3 and enclosed with first bracket, so this is an ordered pair. Say -3 5, this is also an ordered pair. 4 0, this is also an ordered pair. So when any two numbers written in specific order and enclosed with first bracket, then it is called an ordered pair. Then equality of ordered pairs. If two ordered pairs are equal, then their corresponding components are equal. Explaining with example, say one ordered pair xy is equal to say -3 4. This is one ordered pair and this is another ordered pair, and the two ordered pairs are equal, then their corresponding components are equal. That means the first component must be equal to the first component, that is x is equal to -3, and the second component must be equal to the second component, that means y equal to 4. So this is about the equality of two ordered pairs. Then Cartesian product of two sets. At first I am explaining with example and then I will write the definition. I am taking an example with set A 2 3 and set B 4 5 6. Then I will first find A into B. A into B, first is A 2 3 into B. B is 4 5 6. We must write in the specific order. First A and then B. If we change the order, it will be wrong. Then it is formed like this. It is the set of all the ordered pairs. 2 with 4 will make one pair, 2 with 5 will make another pair, 2 with next element 6 makes another pair. Then same way with 3 again, all the ordered pairs 3 4, then 3 with 5, then 3 with 6. So Cartesian product is the set of all ordered pairs in which the first component is from the first set and the second component is from the second set. In every ordered pair we can see, say here, the first component is from the first set, second component is from the second set. Same way we can find B into A. Here B at first, B is 4 5 6. Then set A is 2 3. We must keep write in the specific order. First is B, then is A. Then same way all the ordered pairs, 4 with 2 making one pair, 4 with next element 4 3 making another pair, then next 5 5 2, 5 3, 5 sorry with 5 finished, then with 6 6 2 another pair, 6 3 another pair. The process is same. The set of all ordered pairs from first set to second set. It is the set of all the ordered pairs in which every pair, the first component from first set, second is from the second set. Same way we can find out A into A. A into A, here first is A, second also is A only. So A is 2 3 into again A 2 3, and I'll write all the ordered pairs from A to B. Sorry, A to A only here. So 2 2 first pair, 2 with next element 3, that is second pair, 3 with 2 making the next pair, 3 with 3 making the next pair. So this is how we find the product of A into A. Then again B into B. B is 4 5 6. 4 5 6 into again B itself 4 5 6. So all the ordered pairs from first set to the second set, 4 4 making the first pair, 4 5 4 5, then 4 with 6, then with 5 5 4, 5 5, 5 with the next element 5 6, then with 6 all the pairs again 6 4, 6 with next element 5, next pair 6 with next element 6, 6, 6 next pair. So this is the product B into B. So this is how we find the Cartesian product. Now I can write the definition like this. Definition, it is like this: if A and B are any two non-empty sets, any two non-empty means there are some elements, non-empty sets, then the Cartesian product is given by A into B, in which it is made by all the ordered pairs A into B, such that A belongs to set A and B belongs to set B. It is the set of all ordered pairs A, B, in which A belongs to A, B belongs to B. So we have to write here, mention here, it is for all elements A and B. A belongs to A, B belongs to B. So this is the definition of Cartesian product of two sets A and B. The next point is a relation. In short, if we say, we can say a relation is any set of ordered pairs. Example, I can write one example: a relation set 2, 3 is a pair, 4, 5 is a pair, X, Y, it is a pair, and say 5, 6 another pair. It is a relation, any set of ordered pairs. Every element of the R is an ordered pair. This is an ordered pair, this is an ordered pair, this is an ordered pair, and the set of ordered pair is a relation. This one we can say in short. But to explain in detail, I am taking an example, one set A, another set B, and at first I am finding the product, Cartesian product of A into B. Just now we have discussed, it is made by the pairs in which first element from first set, second element from second set. So 2, 4 making the first pair, 2, 5 making the next pair, 3, 4 next pair, 3, 5 making the next pair. So I have written the set of ordered pairs. That is Cartesian product A into B. Now I'll take all the subsets of A into B. Subset means the collection of elements from A into B. I am going to write subsets of A into B. Collection of elements taking 1 at a time, 2 at a time, 3 at a time, and so on. So if I take 1 at a time, 2, 4, it is a subset. Then 2, 5 is another subset, the pair 2, 5. Every element 1 at a time makes subsets. So I can write more subsets. Then if I take 2 at a time, say first and second, 2, 4 is a first element, then second element, this 2 elements making a subset, and so on. I can write more elements, so first, third another subset, first, fourth another subset, second, third. So taking 2 at a time. Same way taking 3 at a time, 2, 4, 2, 5, next pair, third element. So these 3 elements making another subset, and I can collect more, I can get more collections with taking 3 at a time. Then taking 4 at a time. Taking 4 at a time means this set itself here, 2, 4, I'll just write it, 2, 5, 3, 4, 3, 5. So this what I have written all are subsets. These are all subsets. These are subsets of A into B, and every collection, every subset of A into B, first is 5 and the last is set itself. This is set itself A into A. Now this every collection, every subset of A into B is a relation. Every subset of A into B is a relation. This is a relation, this is also a relation, this is also a relation. So here this is one relation, this is another relation. Every subset is a relation. So now how many subsets will be there? Number of subsets, we know number of subsets, the formula is given by 2 to the power n. And in this case, if set A has m elements, set B has another n elements, then this product will have m into n elements. Cartesian product m into n elements. So total number of subsets we will have here 2 to the power mn. Total number of subsets we will have 2 to the power mn. That is the number of relation. Total number of relations from set A to B is given by 2 to the power mn, where m is the number of elements in first set, n is the number of elements in second set. Here in the first set, how many elements? 2 elements. 2 to the power, first set is having 2 elements, second set is having another 2 elements, so 2 to the power 4. That means we will have here total 16 relations. And then this empty set phi is called empty relation. it is called empty relation. And then this set A into B, this A into B itself is called universal relation. It is called universal relation. So this is about relation on a set. Any subset of A into B, any subset of A into B is a relation from set A to B. Now I can write the definition of relation like this. If A and B are any two non-empty sets, then a set R given by the ordered pair AB in which first component is in first set and second component is in second set is a relation. This is the relation of definition of relation from set A to B. This is the definition of relation. So what we have learned is a relation. In short, we can say a relation is any set of ordered pairs. Any set of ordered pairs is a relation. And then if we have one set A, another set B, and then we will find first Cartesian product A into B, and every collection, that means every subset of A into B is a relation from set A to B. And hence total number of relation from set A to B we can have how many? 2 to the power m into n. M is number of elements in set A, n is number of elements in set B. And phi is called empty relation, and A into B itself is called the universal relation. So this is about a relation from set A to set B. The next is about domain, range and codomain of a relation. I am considering an example. One set A, another set B, and a relation from set A to B given by like this. Then domain is set of all first components of elements of the relation R. It is the set of all the first components. In this relation, what are the first components? First component is here 1, then 2. So all the set of first components makes the domain. This is the domain for this relation. Then range is set of all second component, all the set of second components of elements of the relation R. So what are the second components here in this relation? Second component 5 and then here 6. The set of second components is the range. So this is the range for this relation. And then codomain is always the whole second set. Here the second set is, the relation is from A to B, second set is B, and this whole second set is codomain. So the domain is the set of all the first components of elements of the relation. This is the relation, first component 1 and 2, which makes the domain. The range is the set of all the second components of the elements of R, the second component 5 and 6 here, which makes the range. And codomain is always the whole second set. In this case, it is the set B. In this case, codomain is the set B. So this is about domain, range and codomain of a relation. The last point is writing a relation in different forms. I am taking an example with set A equal to 1 to 7 and a relation R is given by this, like this. It is a set of ordered pairs xy in which x and y are connected by this equation, and x and y both should be in set A. Now I can take x. What are the elements x? X can be any elements from set A. That means 1, 2, 3, 4, 5, 6, 7. It can be any. X can take any value from this set A. Then y is equal to x plus 1. This is the condition given, y equal to x plus 1, which makes the relation between x and y. Then if I take x1, what will be the corresponding value of y? 1 plus 1 will be 2. Then if I take x2, 2 plus 1 is 3. 3 will correspond, 3 plus 1, 4. 4 will correspond to 5. 5 will correspond to 6. 6 will correspond to 7. 7 will correspond to 8. But I cannot take 8. I can take only up to 7 because 8 is not in the set. According to this condition, both the elements must be in the set. Then what is the relation? Relation I am getting like this. 1 related to 2, then 2 related to 3, 3 related to 4, 4 related to 5, 5 related to 6, 6 related to 7, 7 related to 8 cannot take. As I have said, 8 is not in the set, we cannot take. So this is the relation. Now I can explain this with arrow diagram, which is also called Venn diagram. It is like this. Set A, the relation is from set A to A itself. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now here we can see 1 is related to 2, 2 related to 3, 3 related to 4, 4 related to 5, 5 related to 6, 6 related to 7. Then what will be the domain? CoDomain is always the second set. This is the CoDomain of the relation. Second set is the CoDomain. So what will be the domain? Domain is the set of all the first components of the elements of R. So what are the first components? In R, first component 1, first component 2, 3, 4, 5 and 6. So this makes domain. The set of all the first components in the relation, as I have explained in the previous example, previous definition. Range is the set of all the second components of the elements of R. What are the second components? 2, 3, 4, 5, 6, 7. So this is the range. And CoDomain, as I said, CoDomain is always the second set, and here second set is A. CoDomain is set A. Now different forms of writing a set. You see this way of writing in XY, in terms of XY, such that XY something related, XY and related by some relation, and X and Y belongs to A. This way of writing set is called set builder form. It is in set builder form. Writing in XY, a relation writing in XY or writing in AB such that AB related and belongs to some set AB, like that. So this way of writing is called set builder form. And when we list the elements in this way, set of ordered pairs, then it is called roster form. And this way of representing by arrow diagram, it is called also Venn diagram. Venn diagram or also called arrow diagram. That means arrow diagram. That means a relation can be written in three different methods. One is in the set builder methods in terms of XY or AB. Another method is a roster method in which we list the elements, set of ordered pairs, and then this is called roster method. And then the third method, arrow diagram method or a Venn diagram method, it is representing a relation by diagram like this. So this is the end of this lecture, and in second lecture, that will be in video 2, it will be available in playlist. In video 2, I will give the complete solution of exercise 2. Video 2, second lecture, I will give the complete solution of exercise 2.1 from textbook. Then third video, I will give the complete solution of exercise 2.2. 2.1 is about relation, 2.1 is all about Cartesian product of sets, 2.2 is about relations, and in the fourth video about relation, I'll give the solution of questions from miscellaneous exercise on relations and some extra questions, and all this video will be available in the playlist.